Wavefield? Let us look at the resulting wavefield obtained from a typical underground heterogeneity in a typical layered geological environment. The wavefield could be divided into a number of different kinds of waves such as primary and multiple reflected waves, refracted waves and scattered/diffracted waves. The reflected waves originate from the layered boundaries, the refracted waves from boundaries of high contrast, while the scattered/diffracted waves are generated by local heterogeneities. The reflected and refracted wavefields would only slightly be affected by the presence of the local heterogeneities. However, since the scattered/diffracted waves are generated by local heterogeneities, they may be used for the imaging of those heterogeneities. Diffraction imaging. Imaging of the local heterogeneities in 3D space can be performed by a spatial summation of scattered/diffracted waves along the travel time surfaces of those waves. The summation can be implemented using one of the two approaches. In the first step, conventional approach, target waves are stacked along the time surfaces defined by some optimal velocity values. These values are usually estimated by a time-consuming procedure of velocity analysis involving visual examination and interpretation of intermediate seismic images. Recently, an alternative method, a more formal, path integral summation approach, has been proposed. Path integral summation is performed by stacking the target waves along all possible time surfaces having a common apex at the given point. This approach does not require any explicit information on velocities since the required multipath summation is performed for all possible velocity values within a wide specified range. Application of the path integral summation to synthetic and real data shows that it can provide reliable images of subsurface objects close to their true spatial locations. However, the spatial resolution of the images obtained by the path integral summation is usually inferior to those obtained using the fixed velocity. In the subsequent sections, we give a brief description of the main principles of the method and illustrate its application by two synthetic examples. Then, we present 4 case studies demonstrating how the method can be implemented for detecting various subsurface objects located in different geological environments.